Okay, let's have a quick discussion on stability of the aircraft. So before going into that, you have to know the three basic difference between what is stability, controllability and maneuverability. Okay, so controllability, as the name says, the ability of the pilot to control the aircraft. Okay, and maneuverability, maneuver means ability to do stunt. So when the aircraft is doing stunts, it is going to take a lot of stress and air loads, right? If aircraft has the ability to take all the stress and air loads, then it has good maneuverability. Okay. Now stability is a completely different concept. As the name says, stability means if there is any disturbance, can the aircraft be stable in the air? Okay, that is what we have stability. If any disturbance moves the aircraft should return back to original position. That is what we call it as a stable aircraft. Okay, so we are going to quickly have a revision on this. Now, to understand stability, we have to divide the aircraft into three axes. We have already learned it. The axis from nose to tail is longitudinal axis. The axis from wingtip to wingtip is lateral axis. And of course, the vertical axis is vertical. We can also call it as directional axis. Okay. Now, before going into the types of stability, the aircraft should have stability in all three axes, correct? Then only it can be stable in the air. So stability is required in all three axes, not only one or two axes. Okay. Now to understand stability, I have classified that into two classes. One is static and another one is dynamic. Now static means what? Stationary, right? So here we call it as differently. Now imagine there is an aircraft here. Okay. So imagine there is a disturbance that moves the aircraft nose up slightly, some disturbance from below pushed the aircraft up. So what will happen now? The aircraft will get disturbed. Now what we mean by stability is if the aircraft comes back to the original position, in the initial tendency, okay, that is what we call as static. Initially how the aircraft is responding. After a disturbance, if the aircraft get disturbed and then comes back immediately to the original position, there is the initial tendency to come back to original position is what we call positive static stability. Okay, positive static means initial tendency. What is the initial response of the aircraft after a disturbance? And positive means yes, the initial response is to come back to original position. If it is not coming back and going in the same disturbed direction, we said to have neutral stability in aircraft. Okay, if the disturbance pushes the aircraft and the aircraft moves away, continuously moving away from the original path, that we call it as negative static. Okay, neutral static, negative static, positive static. So remember that static means the initial tendency. After disturbance, what is the initial response of the aircraft? If the initial response is to return to original position, it is having positive static. If it continues in the disturbed path, it has neutral static. If it is keep on getting disturbed and moving away from original position, it has negative static. Now this is a theoretical concept. Do you really think the aircraft will come back and stay in the original position and continue the straight level flight? It's not easy. It's not at all easy. Any disturbance, if it moves the aircraft will get disturbed and it will come back, but again it will get disturbed, again it will get disturbed. So it will take some time to settle down for the aircraft, right? So when it takes time, we call it as dynamic stability. Okay, if it takes time to settle down to come back to neutral position, this is the practical scenario. This is what we call as a dynamic stability. The initial tendency to come back is positive and it is static. The initial tendency is static. If it takes some time to come back, that is positive dynamic. What if it is not coming back, it is getting disturbed with the same amplitude, okay, without changing any strength? It is getting disturbed with same amplitude means this, imagine this is a aircraft getting disturbed up and down. Okay, the height where it is going up and down, that's called amplitude. If the amplitude of this oscillation is same, that is neutral dynamic. Okay, if the aircraft is getting disturbed and continuously moving away and the amplitude is increasing, that is what we call negative dynamic. Okay, so to simply put, what is the initial tendency of the aircraft? The initial response after disturbance, that is static. What is the response over time? that is dynamic. In that we have three types. If the response is to come back to neutral position, original position, that is positive. If it is getting disturbed and moved away from original position and not coming back to original position, that is neutral. If it is continuing away from the original position and getting disturbed continuously, that is negative. Okay, if this is clear, we can go into the three types of stability. In aircraft we have three axes, right? Longitudinal, lateral and directional. In all three axes the aircraft should have stability. Okay, how we achieve the stability we will see now. Let's start with the longitudinal. Now to understand longitudinal and lateral stability, let's take this pen as an example. Imagine this is the nose and tail of the aircraft. Okay, if any disturbance moves the nose and tail up, it should come down, correct? Imagine something disturb the aircraft nose up, that means it should come back to original position. Okay, so the nose and tail pitching, longitudinal stability means the aircraft is stable in pitch or what. Now this is about which axis, that is very important to remember. About lateral axis, if the aircraft is stable, it has longitudinal stability. Okay, imagine my two fingers as the lateral axis. If the aircraft is stable about lateral axis, if the aircraft is stable in pitching about this lateral axis, it has longitudinal stability. The opposite of this is, imagine the pen is the wings now. If the aircraft is stable in rolling, rolling is about which axis? Longitudinal axis. Okay, about longitudinal axis, if the aircraft is stable in rolling, that is called lateral stability. Okay, let's go into that. I have drawn some simple pictures for easy understanding. Now longitudinal stability, let's take this view of the aircraft. We know what is CG, what is CP, right? Let's imagine a condition. We have CG forward and CP on the aft side. Imagine something disturb the aircraft like this. Okay, what will happen? The aircraft nose will go up. That means by stability definition, what do you mean by this? If any disturbance push the aircraft to one side, the aircraft should return back to original position. So how it happens is because of this design here, the horizontal stabilizer. Okay, now we have to go to basic understanding of what is horizontal stabilizer. This is how it actually looks. It is a symmetrical aerofoil design. Okay, horizontal stabilizer is a symmetrical aerofoil design. So when you say symmetrical aerofoil, at 0 degree it has same pressure on both sides, so it will not create any pressure difference. There will be no lift in this aerofoil. So at 0 degree it will not create any lift. Okay, because both sides same airflow, same speed and same pressure. How you get lift? When you have an unsymmetrical design, you get pressure difference around the aerofoil. This pressure difference will create a lift, correct? But here in case of this, it has both same curvature on both sides, so it is like symmetrical on both sides. So both sides will have same pressure, so there is no pressure difference and no lift. But imagine something disturb the aircraft now like this. The nose will go up. If the nose goes up, look at this figure, some disturbance push the nose up. If the nose goes up, the tail also like this. Now the symmetrical aerofoil is at a slight angle, correct? Now I have drawn it here also. If the symmetrical aerofoil is at an angle, positive angle, what happens is on the top side the velocity will rise because of low reduction in area. So when velocity rises here, we get a low pressure. Now we get a pressure difference in this aerofoil. Okay, now it will create a lift. Now once it creates a lift, what happens? It will move the tail back up and the aircraft becomes stable. Clear? Let me put in simple words. Imagine some disturbance putting the nose to top. The tail will go to some angles. Now at positive angle, symmetrical aerofoil can produce lift. Okay, and it moves the tail back. So this is how we get longitudinal stability. Imagine if any disturbance puts the nose down. Now the symmetrical aerofoil is at negative angle like this. At negative angle, we have low pressure below and high pressure above. So what happens? It creates a downward force. It creates a downward lift, or we can say down load. At positive angle, the symmetrical aerofoil creates a lift. At negative angle, it creates a down force or down lift, a negative lift. So when any disturbance moves the aircraft down, the symmetrical aerofoil is at a negative angle. It creates a down force and moves the tail back, so aircraft will become straight and level. Okay, so what is very important for us in this is the location of this tail. How much distance it is from the wings. This distance is very important. The more distance you have, more moment we get. Okay, what do you mean by moment? Generally, force acting at a perpendicular distance, right? So if the distance is more, the moment you get will be more. Okay, so the area and also the area of the tail. If the tail has more area, if it is a long tail, you get more stability, or if the distance is more, you get more stability. Okay, these two things are important. Then another thing is the location of CG. If the CG is forward of CP, okay, forward means front side, aft means back side. Okay, if CG is forward of CP, what happens? Imagine if some disturbance moves the aircraft up, the CG is forward, right? So it will pull it back down. Okay, so CG forward is always a good design. So CG forward design, CG forward of CP, or we can also say CP aft of CG. We can say in both ways. So CP aft of CG, location of the tail and the area of the tail, all this will give you a good longitudinal stability. Clear? Now what about wings? Can wings give you stability? What we know about wings, wings is a unsymmetrical airfoil, right? Now when angle increases, what happens? Lift increases in the wings. So if lift, imagine some disturbance push the aircraft. Okay, if some disturbance push the aircraft nose up, the wings go to slight angle. What happens? It increases the lift and it will further push the aircraft up. So wings will not give you stability. Okay, because if any change in angle, wings increase the lift. So wings actually give a instability. It doesn't give you a positive stability. It will give you negative or neutral stability. So in longitudinal stability, the three things that is important is location of wings with respect to CG. I mean the CP aft of CG, and the location of the tail and the length and the area of the tail. These three are very important for longitudinal stability. Okay. Now let's go into lateral stability. Now what I told about lateral stability, with respect to longitudinal axis, imagine my finger as a longitudinal axis. With respect to longitudinal axis, how the wings are stable. Okay, imagine my two finger as a longitudinal axis. Okay, with respect to longitudinal axis, how the wings are stable, how the aircraft is stable in rolling, that is lateral stability. Okay, so when we say longitudinal stability, it is about lateral axis. When we say lateral stability, it is about longitudinal axis. Remember that. Okay, now here we have three simple designs that helps the aircraft to return back to original position after disturbance. Okay, now imagine this diagram I have drawn here. Generally aircraft wings will come with a positive angle with respect to the lateral axis. We call it as dihedral angle. Okay, so when we say stability, we have to consider disturbance. Okay, so when I say lateral stability, let's consider a disturbance attacking the aircraft from the side. So we commonly call it a side slip. Any wind approaching the aircraft from the side. Okay, any disturbance that push the aircraft to the side, what will happen now? Now see this. Now this wing will be like this. Okay, the other side of the wing, this wing, it goes down like this because something rolled the aircraft like this. Okay, I told, right, what is lateral stability? Rolling stability. Okay, any disturbance that rolls the aircraft to one side. When the aircraft rolls to one side, now look at this wing. This wing become flat. Initially it had an angle. Okay, initially the wing is like this, like a dihedral angle. Okay, don't think this much dihedral. For easy understanding, I have drawn it. So once the disturbance moves the aircraft like this, the wings turn like this. Now what happens? Now imagine the aircraft is getting pushed this side. So when it's getting pushed to this side, there is a wind attacking like this. Correct? So there is a side wind that is pushing the aircraft to one side. When it is getting pushed to one side, the wind is attacking like this. So when the wing attacks, this side of the wing will face with more angle to the wind. So what happens? It will push it up. It creates more lift on the wing that is going down. Remember that. Okay, the wing that is going down, or we can say the wing that is slipping into the wind. The wing that is slipping into the wind will create more angle with the airflow and it creates more lift. So what happens? More lift this side, less lift this side, the aircraft will return back. So this is how dihedral help you in lateral stability. Okay, let me put you in simple term. Dihedral means what? A small positive angle with respect to lateral axis. If any disturbance, any side slip, push the aircraft to one side or roll the aircraft to one side, and this side wing will create more angle with the airflow and more lift, so it will turn back. So here the wing slipping into the wind. This is the wing, the downgoing wing that is slipping into the wind, that is having more angle with the wind, so it creates more lift. Okay, this is how we get stability because of dihedral. Now there is another interesting design called keel effect. Now this is very interesting. Now I have drawn one simple example to understand this. Look at this. It is like a small sailboat. Okay, sailboat with a sail. Now what we know about this boat is, from any direction the wind can attack it. This boat will never sink, right? It will only shake left and right, but this boat will never sink because all the weight is here below. All the weight of the boat is here. So this boat will never sink. So imagine the aircraft like that. Okay. Now I have the aircraft here. Okay. Imagine something pushed the aircraft like this. Okay, what will happen? It will go like this, getting disturbed. It get disturbed. Now since all the weight of the aircraft is below, we know that, right? All the passenger, everyone, cargo, everything is below. Passenger is somewhere here. So most of the weight of the aircraft is distributed below the CG, right? If you take this figure, most of the weight of the aircraft is distributed below the CG. So what happens if any disturbance push the aircraft like this? It will go up. Then because the weight is below, it acts like a pendulum and it will pull it back. You know pendulum, right? Like a ball hanging in a string. When you push it one side, it will come back. So why it is coming back? Because the ball is hanging in the string and the weight is below, it is coming back. So aircraft also behaves like that. If any disturbance push the aircraft from side, okay, it will swing, and since all the weight is concentrated below the CG, the aircraft will return back. This is what we call as keel effect. So for this to be effective, what we should have, the wing should be above, it should be a high wing aircraft, and all the weight should be concentrated below the CG. The maximum weight should be concentrated below the CG. When you have this design, if any disturbance push the aircraft to one side, the aircraft will swing back like a pendulum. That's what we call keel effect. So know that the location of CG is very important. The weight of the aircraft is below the CG, and this area where the weight is less, we call it as keel area. Okay, where weight is like similar to the sailboat, where you have the sail above, same like that we have an area here that acts like a sail, that is having very less weight compared to the weight below the CG. So this area is called keel area. So keel area should be above CG and maximum weight is distributed below the CG. If you have this design, the aircraft will act like a pendulum when there is any disturbance. Okay, so these two designs will give you dihedral and keel effect and the weight distribution. Okay, these things will give you lateral stability. There is one more thing that is also very important, sweep back. Now sweep back design is very important because it gives two stability, both lateral and directional. So let's see the same example. Imagine something pushing, some disturbance, side slip, pushing the aircraft to one side. Okay, so the side slip is a common name given in lateral stability for a disturbing wind. If any wind comes from the side and slips the aircraft, we call it a side slip. So imagine something disturb the wing like this from sides. So what happens now? This is sweep back, right? This is the angle with respect to the axis, that is sweep back. If any disturbance push the aircraft like this, now the wind will attack like this, correct? It's like imagine I am pushing the aircraft this side, so wind is attacking this side now. So because the wind is having more angle with the wings here, it create more lift on this wing. Compared to this wing, the air will not mostly come this side, and even if it comes, it will be having parallel angle with the wings. But here the wings are attacking the wings. You can see the wind is attacking the wings with more angle, almost 90-degree angle. So this wing will create more lift. So if any disturbance push the aircraft to this side, this wing will create more lift and pulls it back. So this is how we get lateral stability with side slip in a sweep back wing. Okay, this is how sweep back gives you lateral stability. Now how it gives directional stability. So what we learned about directional stability is our stability about vertical axis, directional axis, right? So if any look at this pen now. Now if any disturbance push the aircraft to one side, now look at this, is very easy to understand directional stability. Imagine any disturbance push the aircraft nose to one side, the same disturbance will attack the tail also, right? The aircraft will return back. Now this common phenomena you can find in meteorology department buildings. On the top of the building you will find one arrow. You will find one arrow on top of the building of weather monitoring areas. What this arrow will do, whichever direction the wind comes, the arrow will turn that direction. like the same example, whichever direction suppose imagine the wind is coming like this and attacking the arrow. The same wind will attack the tail, right? The arrow will turn, pointing towards the wind direction. So it tells you which direction the wind is attacking. Now your aircraft also behaves like that in vertical stability. If any disturbance disturbs the nose like this, when the same disturbance attack the tail will turn back. Okay, so the ability to come back to original position, that is stability, right? So in directional, how we are getting, any disturbance hits the nose, the same disturbance can hit the tail. So here the tail is very important. If this side of the tail has more area, you get more stability. Understand? So that's what I have drawn here. You can see where it is. Yeah. So after the CG, here after the CG, okay, after the CG, how much area of the fuselage and how much area of the fin is called the vertical stabilizer, okay, how much area of the fin and how much area of the fuselage after the CG. If you have more area after the CG, if any disturbance moves the aircraft, it can easily move the tail also, okay. So here the area of the aircraft fuselage after the CG and the area of the fin, these are very important. When you have more area, you get more vertical stability, okay. The wind can easily attack here, okay. More area means it can easily attack. In some aircrafts you can also find extra fins here. It's like this, like this. These are called dorsal fins and ventral fins. This increase the area of the fin, simple, okay. Any disturbance that moves the nose can also, okay, let me put it very clearly. Any disturbance that moves the nose, when it attacks the tail, if the tail has more area, it can take more air and turns back easily, okay. That's what we call vertical stability or directional stability. How we are achieving it? After the CG, there should be more area, and this is also we can call keel area, okay. The keel area, that is effective area or keel area. More keel area after CG and more fin area. This will give you directional stability. In lateral, what we discussed, when you have more weight below CG and more keel area means similar to this sailboat, okay, the empty weight or the less weight portion, that is called keel area. When keel area is above CG and weight is distributed below CG, the aircraft acts like a pendulum. That is lateral stability. In vertical stability, if the keel area is after the CG and more fin area you have, you get more stability, okay. So don't get confused with the word of keel. Keel means that generally commonly called area, effective area, okay. If you have more area after the CG, you get good stability, vertical stability. Here, if the area is empty area is more above CG and more weight is distributed below CG, you get good lateral stability, okay. Now I told about sweep back, right? Sweep back also gives you directional stability. Now look at this figure. So directional stability means what? If anything disturbs the nose like this, we'll turn it back. Now imagine the nose is here, okay. Yes, this is the nose and tail. Imagine this is the sweep back. Imagine something disturb the nose like this. What happens to the sweep back now? The sweep back becomes straight like this. Before it was like this, okay, and the sweep back was angled. Now something disturbed the nose like this and the sweep back turned like this. Now what happens? Initially the sweep back was like this, okay. Now imagine this pen as the sweep back angle. This is the sweep back wing. When anything disturbs the nose, the sweep back turns like this. So it travels faster, and now the air is attacking like this, right? Imagine this is a sweep back wing, okay. This is not the aeroplane now, this is the wing, sweep back, slightly angled wing, okay. Aeroplane is going forward, this is nose and tail. Imagine something disturb the aircraft from sides, something attack the nose from side. So nose will turn like this. Once the nose turns like this, the sweep back also turns like this. Now you see how the sweep back is turning, it is becoming a straight wing now. It is traveling faster and it's becoming straight. So what will happen? Initially sweep back was like this, now it became like this. So more air will attack with more angle and the sweep back will turn with more speed. So more speed and more angle, more airflow attacking it on this side, okay. This will create more drag on this wing, okay, more drag on this wing. Whereas the other side, the wing will just go down like this. So here the drag will not be that much. Here the wing is facing the airflow straight, perpendicular. So it creates more drag on this wing. This drag will pull this wing this side, so the aircraft can turn back. Okay, so initially some disturbance pushed the nose this side, the sweep back turned like this. Once the sweep back turned like this, the air is attacking straight. It creates more drag on this wing, so that wing will pull the aircraft and the aircraft will turn back. So this is how we get directional stability with the help of sweep back. So directional stability, how we are getting sweep back and keel area after CG and more fin area. Okay, how we are getting lateral stability? Same, sweep back will give you lateral stability. Then keel effect, that is keel area above CG and dihedral. Okay, and longitudinal stability, how we are getting? The location of the tail, the distance of the tail, the size of the tail, and location of wings with respect to CG. Okay, these are the three stability and the designs associated with the stability. Okay,